The next thing we want to take a look at in our study of graphs are a special type of graphs called trees. A tree is a connected graph that has no simple cycles. Remember, a simple cycle is a path that begins and ends at the same vertex without repeating any edges. If that's not possible, it's called a tree. If every connected component of a graph is a tree, we call it a forest. In other words, a forest is just saying I have a bunch of trees and I put them together and consider that a graph, but their individual connected components are all trees. So for example, here is a tree. It is not possible in this graph to draw a simple cycle. If you begin at a vertex and you come back to that vertex, the only way to do so is by repeating an edge. This graph, however, is not a tree because it is possible to start at one vertex, walk along several edges without repeating any edges, and come back to the same vertex. As such, the red path now, anywhere along this that you start, for example here, you can walk along this, come back to where you started without having repeating any edges. So this is not a tree. The same procedure is not possible in the graph above, so it is a tree. It would be nice to have a characterization of trees that was maybe easier to implement than this kind of abstract definition that it is not possible to construct a simple cycle without repeating edges. So the following are all equivalent. In other words, if you have a graph which is connected and simple, in other words, it's not a multigraph, with n vertices and an edge set e, any one of the following conditions will immediately imply all of the others. First, it's a tree. It has no cycles. Or it has exactly n-1 edges, where n was the number of vertices. Or, given any two vertices, there's exactly one simple path connecting them. Or, if there is an edge set, which is non-empty, then the deletion of any single edge will create a disconnected graph. If you have any one of these conditions, it immediately implies all the rest. We'll partially explain, but without fully proving this result. So suppose a graph has a cycle, in other words, it's not a tree. Then it does have a simple cycle. Okay, so let's call that simple cycle this, v1 through vn, and then it comes back to v1. Okay, all the vertices are distinct except possibly the first and last. So why, if a graph has a cycle, does it necessarily have a simple cycle? Well, imagine somewhere in the intermediary here was like v5 happened to be the same as v10. In other words, the path goes from v1, eventually ends up at v5, goes through some more steps, but v10 it's back at v5, and then it comes back to v1. You could just cut out whatever it did in between those two occurrences of the same vertex. So if the same vertex appears twice, other than the start and stop that is, then that would be some sort of loop along the way. And if you simply don't do that, then you will go from one vertex to itself without repeating any vertices. So any graph that has a cycle has a simple cycle. So let's suppose the graph isn't a tree. In other words, it does have a cycle. Well, then it must have a simple cycle. And here it is. So these are all different vertices except for the fact that it starts and ends at the same place. So between any two distinct vertices in this list, there are in fact two different paths. Okay, so imagine I pick two vertices in this list, for example, v2 and vn. The way I could do a path is I could go from v2 forward along this path and hit vn. Alternatively, from vn, I could go to v1, and then from v1 go to v2. And since all of these vertices are distinct, this one does not use v1, and this path would, so those are different paths. So any graph that has a simple cycle, if you pick 2 points on that cycle, there are in fact two distinct paths that get you between those two vertices. So if a graph has a cycle, it's possible to find vertices with two paths connecting them. And that's a link between the first and third item in this list. If it does have a cycle, then there are two vertices with more than one path connecting them. So 1 and 3 are clearly linked. Also, if you have a cycle, so I have a bunch of edges that you can imagine going around in a circle connecting a bunch of vertices, if you remove any one of those vertices, you haven't actually disconnected anything. And that's a way to see that item 3 and item 4 are connected. If there is a cycle, then I can remove an edge without disconnecting anything. So 1 is connected to 4, 1 was already connected to 3, so 3 and 4 are also connected. Now, furthermore, we have already established that any connected graph with n vertices must have at least n minus 1 edges. So suppose a graph has exactly n minus 1 edges. Now, if you remove an edge, you don't have enough edges to be connected, which means item 2 is connected to item 4. If a graph has exactly as many edges as needed to be connected, then yes, if you delete any edge, you must now be disconnected. So item 2 and item 4 are the same, and we've already established item 4 is at least related to items 1 and 3. So while not a full proof, all of these ideas are clearly interlinked. And in fact, they are all logically equivalent. Any one of these will immediately imply the rest. Similar to our discussion of trees, there is another notion of a spanning tree. If G is a connected graph, a spanning tree of this graph is a subgraph that is a tree, but also must contain every vertex. So it's a tree because it's called a spanning tree, but the word spanning is used to imply that it does in fact touch all the vertices that the graph began with. So for example, here's a graph. Can we find a subgraph that is a tree but contains all of the vertices? Here's one, okay? So I have rescaled the graph to be smaller because we're going to present several options, but it has all of the same vertices. How do we verify that this is a tree? Well, it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. And we established on the previous slide that if you have n vertices and exactly n minus 1 edges, you are a tree. So from the 12 vertices, it was possible to keep 11 edges, still remain connected, still have all of the vertices we began with, so this is a spanning tree. But so is this. It's got all the same vertices, and I kept 11 edges and made a tree. So is this. So there are multiple ways sometimes to make a spanning tree within a graph. Which brings up a question of a minimum spanning tree. So suppose we have weighted graphs, so all the edges have weights on them. What if I want to find a spanning tree of minimal total weight? This is related to problems we've discussed before. If you have like a communications network and you want to lay fiber optic cable to connect them, well, you want it to all be connected, so you want to make some sort of connected graph, but you want to do so as cheaply as possible, so you don't want any redundancies. So for example, you want every edge you lay to be critical. You don't want it to be possible to remove an edge and still be connected. In other words, you want to be a tree. But of all of the costs of laying all the various cables, you want to do it as cheaply as possible. So you want to build a tree where every edge is vital. In other words, no edge can be removed and remain connected. You want to touch all of the vertices, because that was the whole point, and you want to do so as cheaply as possible. You want a minimal spanning tree. Well, if a connected graph has finitely many edges, there are only finitely many spanning trees. This is a very simple, straightforward result. If there are n edges, then there is some number of edges that a tree will contain. Okay, so suppose there are n edges and k vertices, then any graph with k minus 1 edges will be a tree. So of the n vertices, I can choose k minus 1 edges and maybe have a tree and maybe not. Okay. In which case, there are finitely many subgraphs with k minus 1 edges, so there are finitely many trees. So therefore, of all the finitely many spanning trees, one of them is going to have the smallest total weight. So if all of the edge weights are actually different from one another, it turns out there's exactly one minimal spanning tree. If I list out all the spanning trees and the edges maybe duplicate weights, it's theoretically possible that I could have two distinct spanning trees whose total edge weights are actually equal. Maybe they're the smallest, but there's two different ones that are the same smallest value. What can be shown is that if all of the edge weights are different from one another, then in fact, there is a unique minimal spanning tree. So let's take a look at an example. Okay, your company has 5 data centers, we'll call them A through E. And the cost of connecting various data centers to one another has been researched and is given by the following chart. If I want to connect data center A to A, well, that doesn't cost any money because it's itself. But if I want to connect A to B, that costs $50,000. Okay, I'm not bothering to write this entrance here because A to B would be the same thing as A to B this way. So here are all the various costs of connecting data centers. So what's the cheapest way to connect them all to one another? In other words, what's the minimal spanning tree that I can extract from this information? Okay. So we are only making a spanning tree. In other words, if we remove any single edge, the result would be disconnected. So there's no redundancy in case one data center goes down. That would be something that involved two connectedness. In other words, can I start removing vertices and their associated edges while remaining connected? That's where you want redundancy in your network, but we're not addressing that here. So we're going to draw that scenario as a complete graph with edges weighted according to the costs from the previous chart. So here are the 5 data centers, A through E, and the various costs from that chart on the labeled edges. So for example, constructing an edge between A and B costs 50. So can we find a spanning tree of this complete graph that minimizes the total edge weight? Now there are only 20 edges total. Okay, there are 5 vertices, and I know between any 2 of them I can construct an edge. So of 5 vertices, choose 2, and those will always create edges. So there are 5, choose 2, or 20 edges. Any tree will have 4 edges in it. So of the 20 edges, if I keep 4 of them, maybe I have a tree, maybe I don't, but there's only 20 choose 4, which is 4,845, ways to choose 4 out of the 20 edges. Then of all of those 4,845 things, you can actually ask which one of them are actually spanning trees and which ones are not. I mean, for example, if I kept this edge, this edge, this edge, and this one, so 30, 65, 60, and 80, vertex C is still totally disconnected from the edges I kept, so that doesn't actually make a spanning tree. If, however, I keep all of the edges, coming out of vertex A, 30, 60, 75, 50, that does actually make a spanning tree. Is that the cheapest of all the spanning trees? I don't know. But what we could do is we could program a computer to make all 4,845 choices of 4 edges out of this, check which ones are trees. For each one, sum up all of the associated edge weights, and then find the one that was smallest. So in this example, it turns out that just taking the 4 cheapest edges actually results in a spanning tree. So if I just keep the 30, the 40, the 50, and the 45, the 4 cheapest edges that are in here, that will actually be a tree. And since they're the 4 cheapest edges, that must be the cheapest possible spanning tree. So if I keep those, okay, we actually have a spanning tree. All of the vertices are connected, and since it was the cheapest edges, the cheapest 4 edges, that's going to be the only way to do that, or the cheapest way to do that at least. That's not always going to be the way to find the solution, of course. There's a nice visualization of trees that we can discuss. So if G is a tree and you pick any vertex, we'll call it V sub 0, that's in the tree, you can call that the root of the tree. We place that at the top. I mean, we call it the root, but we put it at the top, not at the bottom. And then inductively, if some vertices have not yet been drawn, since the graph is connected, some of the unused vertices must be connected to something that's already been drawn. So we start the procedure just by placing V0 at the top. Some vertices have to be connected to it because otherwise this vertex would be disconnected. So similarly, if you've drawn a whole bunch of vertices, if some still haven't been placed, at least one of them has to be connected to something you've already drawn, otherwise you'd have 2 disconnected components. So if an unused vertex is connected to any vertex which has been placed, it can only be connected to 1. If it was connected to 2 vertices that were already placed, I would be able to draw a cycle. So place this on a level underneath the vertex that it's connected to and try again. So the result is a progression of levels, okay, starting at the top with the root, where a level is connected to exactly 1 vertex in the level above it and some quantity of vertices in the level below it, possibly none, possibly more than 1. For example, the tree at the beginning of this section was this, okay? Let's, for the sake of argument, begin with vertex B as the root. So I stick it at the top. And now I ask, are any vertices connected to B? Why, yes. A is connected to B, so I put it on a level below. And now I ask, are any vertices that I have not drawn connected to A or to B? Yes, vertex D is connected to B, so I put it on the level below that. I still haven't placed vertex C, E, and F, and I ask, are any of them connected to any vertex that's already been drawn? Yes, vertex C is connected to vertex D, vertex F and vertex E as well. And now what we have is a visual representation of a top level, which is B, connected to the next level, which is A and D. These things are connected to the next level, C, F, and D. A is not connected to anything on the level below, that's okay. D is connected to multiple things on the level below, that's okay. But what does happen with this representation is that everything is only connected to one thing above it. C to D, F to D, E to D, D to B, and A to B. And you can do this by picking any vertex in the tree. Pick any vertex you want, and you can sort of stack them in this hierarchical construction. F, below it would be D, below D would be C, B, and E, and below B would be A. So that would be another way you could present this same graph, but rooted at F. Okay, you would have F connected down to D, to C, and to E, but also to B, and then B is connected to A. Notice that by choosing a different root, we actually have a different number of levels. Okay, so by rooting it at B, we had 1, 2, 3 levels. By rooting it at F, we actually have 1, 2, 3, 4. But still, these are just different presentations of the same graph by choosing a different root. Along with roots, there's a notion of parents and children. So in the presentation before, we picked a root. If a vertex is connected to another, depending on what level they're in, we call one the parent of the other or the child of the other. If it occurs in a higher level, it's the parent, and if it occurs in the lower level, it's the child. Okay, so the root will be the only vertex with no parent, and every other vertex has exactly one parent, but possibly multiple children. Any vertex that's not of degree 1, however, will have at least one child. Okay, if it's of degree larger than 1, it can only have one parent and it's connected to it, but since it's of degree larger than 1, it has more edges, which must then connect to children. Okay, so other than the root, which has no parent, any vertex of degree n has a single parent and therefore n-1 children. There was, however, nothing special about which vertex we picked to be the root. Any vertex could have been the root. So the same tree from before was originally presented like this. If we root it at vertex D, we would get this presentation. And you can see that from this picture. D is connected to B, C, F, and E, and then B is connected to A. So D is connected to B, C, F, and E, and B is connected to A. Could have also drawn it like this. A is connected to B, to D, to C, F, E. A is connected to B, to D, to C, F, E. So the notion of parent versus children actually depends. Okay, so in this presentation here, for example, A is the child of B. But in this presentation, B is the child of A. So it will depend on what vertex you pick as the root, which are parents and children of what. Okay, so the notion of parents and children is not something that's really intrinsic to the graph. It just helps us describe it based on how we want to draw it. But there's nothing special about picking which vertex you want to be the root, and therefore nothing special about which vertex is a parent or child of its connected vertices.